So here we're going to look at the final questions in this chapter, exercise 13.3. Pendulums, and the key formula we'll be using is this: the period t is equal to 2 pi times the square root of L over g, where L is the length of the pendulum from the fixed point to the center of gravity, and g is gravity. So question 1, what is the period of a pendulum of length 2 meters at a place on Earth where gravity is equal to 9.81 meters per second squared? So again, as always, we'll identify our information. Gravity is 9.81 meters per second squared. The length is 2 meters, and we're asked to find the period t. So we use this formula. T is equal to 2 pi times the root of L over g. That gives us this when we substitute it in, and we get an answer that the period is 2.84 seconds. So very straightforward, just getting used to using the formula. Second question, a simple pendulum of length 0.8 meters makes 50 oscillations in 90 seconds. What is the acceleration due to gravity at this location? So again, we break it down. Our length is 0.8 meters. It makes 50 oscillations in 90 seconds. So from our previous work in section 13.1, we know that the period t is the time taken over the number of oscillations. So that's 90 seconds for 50 oscillations. So that's 1.8 seconds. So that's another way to get our period. We are asked to find the acceleration due to gravity at the location. So we need to find out what g is. So this algebra is a bit tricky, and it's one of the more difficult things to identify because we have to get this g, which is under a square root, which is beside a constant, which is on the other side of the equation. So what we do, first off, we square both sides. That gives us the whole side squared. So t gets squared, 2 pi gets squared to give us 4 pi squared, and this gets squared, which gives me just L over g. Then I want to write it as a single fraction. So I take t squared equals 4 pi squared L, that's my top line, over g. And again, that's fine, I can do that, that's just normal algebra. So then I multiply both sides by g, so I get t squared g is equal to 4 pi squared L. Then I divide across by t squared, so I find out that gravity is equal to 4 pi squared L over t squared. So then I was running out of space, so squashing in the corner, that's the hard part. I just substitute in my information. 4 pi squared is a constant, just remember to square it. My length is 0.8 meters, which is also squared, and that's over 1.8 seconds, which is squared. Sorry, that should not be squared. There should be no square there, but that is the correct answer. So I think I was thinking of meters per second squared, but that one shouldn't be there. So that is just, as you see it here, g is 4 pi squared times 0.8 over 1.8 seconds squared, which gives me 9.75 meters per second. So that's the first couple of questions. Question 3. What is the length of a pendulum whose period is 2 seconds? And we're told to take gravity equal to 9.8. So we're asked now for the length. So the period t is equal to 2 pi times this. That's our usual formula. Again, we square both sides to give us t squared is equal to 4 pi squared times L over g. The square root is gone because it's been squared. Again, we write it as a single fraction, so we get 4 pi squared L over g. We again multiply both sides by g to make it linear, so we got rid of the fraction. So t squared g is equal to 4 pi squared L over g. 4 pi squared L. Then I divide across by 4 pi squared, so I just get L, so this is now written, so this is t squared g in terms of L. So we have, this is now my formula to find the length. So here, the period is 2 seconds, gravity is 9.8, so my length is t squared times g over 4 pi squared, which gives me a length of 99.29 centimeters, or 0.9929 meters. Again, I've up here, just a little note, I've written t squared g a couple of times. That was just the way I was doing it. Typically, you'd write tg squared. That's a bit more standard, like you'd say 4x squared. You wouldn't say x squared 4. So say something like gt squared, 4t squared is a bit more standard. It doesn't really matter, but you might see it other places, but it's the same thing. So I've written t squared g. Typically, you write gt squared. Similarly, over here, you probably put g then t squared, but it's a very minor issue. Final question, question 4. The period of a simple pendulum on the surface of the Earth is 0.4 seconds. What would its period be at a height above the Earth equal to 3 times the radius of the Earth? So again, a diagram is very important and it will stop you making a mistake. The period, we're told t is 0.4 seconds. The height above the Earth is 3 radiuses. So we have 1 radius to get to the surface of the Earth, and then we have 3 radiuses above it. So that is, again, you'd easily just take the height is 3 times the radius, but it's actually 4 because it's 1, 2, 3, 4. It's 4 radiuses, 3 radiuses above, and 1 radius in the first place. So again, this is linking back in our other sections because we're at the end of mechanics now. So the force due to gravity, the acceleration due to gravity, sorry, is gm over r squared. M is the mass of the big planet, and r is the radius or the distance. So it's the radius if this was going around in a big circle rather than the radius of the Earth. So g is proportional to 1 over r squared because g and m are constants. So g changes with 1 over r squared. So here we're told that the first radius, the one on the surface of the Earth, that's the radius of the surface of the Earth. And then our second radius, the one all the way out to the object, that's 4 times the previous one. So the gravity on Earth, that's proportional to 1 over r squared. That's what we got above here. So the gravity at my point, so this is Earth, that's my first radius, this is my point, that's my second radius, that's going to be 1 over 4 times that. So that's my change. I've gone 4 times further away, so it's going to be 4 times this. Because it's 4 times the radius of Earth squared, I probably should have brackets in around that, so we get 4 RE all to be squared, which is 16 RE. So just be careful with that. I should have brackets around that whole thing there. In fact, I'll put them in. So we have now that the gravity of the point is proportional to 1 over 16 times the radius of the Earth squared. So if we look at the first one down to the second one, gravity is 16 times smaller at this point. Further away, this point 3 times above the radius of the Earth, that's 16 times less gravity than the point on the surface of the Earth. From our previous work, we know that the period changes with 1 over the square root of gravity on Earth. So when the point is on Earth, we get this relationship here. So we take 2 pi as constant, the length is constant, so it only changes as gravity on Earth changes. Here we have the gravity on Earth is 1 over r squared, so we substitute that in. So we have the square root of 1 over r squared. And again, I skipped a couple of lines here, but if we look at the square root of 1, that will be 1. If we look at the square root of r squared, that will be r squared. And, well, I'll just talk to the algebra down here and it'll make more sense. So at the point further away, we use this relationship. So t is proportional to 1 over g on Earth. And at the point, t period is proportional to 1 over the gravity at the point. We know the gravity at the point is this down here. So we substitute that in. Gp is replaced by this. So we have the square root of 1 over 16 re squared. When we work this out, we got the top line in black, and I got this bit under here I wrote in blue. So this is the square root of this whole thing. So we can put that as the square root of 1, which is 1, over the square root of 16 re squared. Square root of 16 is 4, square root of re squared is re. So again, 1 over 4 re. So I'm dividing by a fraction, so I invert and multiply. So that's what's happening here. So the 1 from the top multiplied by this inverted. So I get that the period is 4 times what it is on the Earth. So I did the same up here. So that same algebra, square root of 1, square root of r squared, invert and multiply. So you get the period is only proportional to the radius. Then at this point further away, the period is proportional to 4 times the radius. So then to tie these two together, the period is 0.4 seconds on Earth. So we have 4 times this, 4 times what it is on Earth. So we get 4 times 0.4, which gives us an answer of 1.6. Now there is a lot of work here and it is quite confusing, but you can kind of break this thing down. And what you find out from doing a question like this is if you were 10 times further away, so if you were 1 and then you were 10 times away, so 9 times the height, so 9 times the thing on the planet, you would be 9 times. So instead of being 4 times, you would be 9 times. So 4 ended up with 4, 9 would end up with 9, and you just have 9 times the period. If you were 10 times away, you'd end up with 10 times, so it would be 10 times the period. So there's a lot of work here, but because this thing is done in general, we can kind of shortcut. This is how it works, this is where it comes from, this is the right way to do it. But if you're looking for a shortcut, we were 4 times longer, we'd have 16 times the gravity because of this relationship, and then because of these relationships, you would again, you square it, you square root it, it comes back. So we were 4 times further here, and we just multiplied it by 4. So long story short, if you get a question like this, if you're 7 times above the surface of the planet, then multiply the period by 7. Because this thing is all done in general. The only thing that changes is 4, it gets squared, then it gets square rooted, and then you multiply by it. So that's where it comes from, that's how it is, but it does reduce overall to be quite an easy problem.